Okay, so drift velocity. Two equations that we're going to use. One is current is charge divided by time, and then the equation for drift velocity, current is NAVQ. Okay, our drift velocity equation. Now, imagine we have a thick piece of wire that is going into a thinner piece of wire. So we have a large surface area and a small surface area, and our current is flowing along this wire. So really that current is going to be made up of many free charge carriers flowing in this direction, each carrying charge Q. There's a number of free charge carriers, and then we've got the current that's flowing there and cross-section area of the wire here, and that's going to affect the velocity. So one thing we know is that these two pieces of wire are connected in series. So being connected in series, the current is going to be the same here in the larger piece of wire. The current is going to be the same as in the thinner piece of wire because they're both connected in series. So the current is going to be the same. It's constant. What else is going to be a constant in the drift velocity equation? Well, being the same material, same type of metal, N is going to be constant as well, and the charge that's carried on each charge carrier, Q, is going to be constant because the charge carriers are going to be electrons. So I, N and Q are all going to be constants. So if I rearrange the equation, I divided by NQ is going to be A times V. Now, this side of the equation, all of this is constant. Okay, so that's going to be all these three. The product of this is going to be the same before as it is afterwards. So that means that cross-section area before, let's call it A1, and the velocity before, V1, is going to be equal to I over NQ, which is going to be equal to the cross-section area and the velocity afterwards. So what I can do is I can get rid of the constant bit there in the middle, and I can say A1 V1 is going to be equal to A2 V2. Okay, to put it rather crudely, I can say that if the cross-section area decreases, that must mean that the velocity is going to increase to make the same product or the same number. Okay, and in the exam they're probably going to ask you to take that a step further and to put a calculation or put numbers, which if it's cross-section area is halved, a half of A, it's going to mean multiplying by 2 times V. So the half here cancels out, 2 times V, a half A, we get is the same as A times V. Now one step further would be to take that and talk about diameter, which is probably what they're going to do in the exam. They won't talk about cross-section area, they'll talk about diameter. But let's keep this easy for the moment. If we go with this concept here, cross-section area decreasing, velocity is going to increase, and and we go back to the diagram, imagine that this is water flowing down a pipe. It's fairly easy to imagine that the velocity here is going to be quite low, and when we have this decreasing cross-sectional area, or this restriction, we know that if it was water, the same amount of water flowing per second through this pipe means a lower velocity, and through this pipe means a higher velocity. Okay, that's drift velocity. I see it very much being like water flowing down a pipe.